In the next unit, we'll talk about text indexing. And I put a subtitle, Searching Whole Genomes, because that's one big application where these techniques are used. We will not speak about this particular application in detail, but it's the motivation for many things behind this. We've talked a lot about string matching in the last 2 units, so you know that problem by heart now. And this time we take a similar, the problem is a similar flavor. We search for patterns in a long text, but we'll allow ourselves to spend time pre-processing the text. So many things that will be done in this unit take the whole text and assume that it doesn't change. Then we take our time to look at that text very carefully. And eventually, once we're done with this pre-processing part, all the queries on the text are very fast. We'll discuss some very simple approaches first. That will probably eat most of today's session. And maybe we'll talk about suffix trees too for today. And then tomorrow we'll talk about their fancier applications and eventually also how to construct them. I should say that this is my favorite unit for this class because it, on one side, has very fundamental and elegant data structures like suffix trees, and it also includes some of the most recent results that we talk about. The last parts are all invented in the new millennium. Now that might not sound very recent, but if you compare this to other fundamental algorithmic problems or data structures that we've discussed, that's fairly recent. Which also means some of these topics have not found their way into the standard textbooks. That's another part while this it was a bit harder to find good literature for this. So pay close attention. The notation I use is also not completely standard because nothing has as much settled and has been established for this topic. Now I scared you a little bit, I guess, but I bet you'll like it, and we'll go through it slowly. The setup is text indexing. As I said, we try to find a pattern in a text, the same as for string matching, but the difference is that we consider the text to be fixed. So we can spend a lot of time to pre-process the text, and then not just one, but usually many patterns arrive over time, and we have to find them in the text. If there's only one pattern, it's not clear if text indexing is the right approach, because usually that pre-processing is fairly expensive. But if you envision that there will be many queries, then this can lead to speedups that are not achievable with anything else. The name of this game, text indexing, comes from, I have that on another slide. Indices are usually used in books. That's the thing at the very end where you can find words, and then it points you back to where in the book does that occur, where is that explained. And we'll use something similar. The name surely comes from that idea. And well, if you care, it means one who points out. So it's always something pointing back to positions in the text. There's many applications that use text indexing in one way or another. All search engines, web search, are text indexing in some sense. They do a lot more on top of that. They don't just find exact matches, but that's how they started. More specifically, dictionaries are a specific form where you're only looking for specific words in typical cases. And the more interesting areas are the ones where text is only in a more remotely way what we're looking at. DNA sequences are a form of text because they're a sequence of symbols, but there's no such notion as words. There's no spaces or white space. And for those, suffix trees and their relatives will be very important. And really, almost anything is a text. Databases are sort of a text collection if you want, so it's applicable in many places. Now here's the original version of an index from books. Is what we would nowadays call an inverted index. It's inverted because it lists individual words and points back to the text, as opposed to listing all the listing all the text in the document and then trying to find positions there, words in there. So it's a list of keywords. In a book, you usually don't list all the words that ever occur, but only the important ones. And creating such a good index is actually a very time-intensive process and needs someone who's really capable of finding the right things to include. But what it is it points from the keywords back to the page numbers where it occurs. And often the pages are sorted by significance in some way. An important assumption for this kind of index to work is that we're only searching for this predefined set of words. If you ever search for anything else, the index won't help you. If you're searching for just part of a word, maybe not as likely in a book, the index won't help you. There's no way to take a part of a word and find where that occurs in the text. So if you think back for string matching, I said it's whenever you can hit Control F to search in your text editor or on the website in the browser, you can type anything. It doesn't have to be a whole word. So this doesn't solve this general problem. But for texts like books, you will usually look up the concepts in a textbook, so there the assumption is fine. Now to make this a little more specific, so this was in books. This is more abstractly in computer science. If you have a text given as a sequence of words, you can collect all those words and build an inverted index for all the words to keep things a little simpler. What's typically needed to make this effective is take into account that the words are not just arbitrary sequences of characters, but come from a natural language. So there's things going on that are called stemming. You try to go from a derivative form of a word back to the primitive form or the infinitive or the singular, etc. But we'll ignore that part. What remains to be done is you have collected a list of words, and for each word you know where it occurs in the text. So the way to think about this is you read the text once, you walk through the text once, word by word, and whenever you find a word, well, you currently are at its position, so it's easy for you to remember where this word occurred because you're just there. But you would have to store something, some data structure that allows you to look up words later. So that's the algorithmic question behind this. How should we store this mapping from words to positions? So to be specific, let's take our two examples. And they would both map to typically a list of indices. So that could be the 5th word and the 10th and the 20th, and this could be here, the cat goes somewhere, whatever, I don't know. It's a text with lots of cats. I guess you get the idea. Now I use this symbol. What we're storing here is really a dictionary. Almost in the sense we had it. There's keys and there's values. The only difference is we need a list of values, not just a single one. But we can define our value type to be a list of something, and then it's a single value in that sense. What you have not seen in this module is a good data structure to represent the specific types of dictionaries that we're using here. So a simple option would be you take a generic dictionary data structure. We've seen binary search trees briefly. You might also know hashing. That would also work well in this case. But we can do something better for the special case because our keys are strings. All right. So here's the first question, which will determine how much time I spend on the next slide. All done? If you are typing, refreshed your memory. Okay, so there's roughly half who haven't heard the term, and another third who don't remember quite so well. And well, an eighth or so, almost the remaining ones. So sorry for the eighth of you for whom this will be a bit boring. It's only one slide really. So if you've never heard of tries, it's pronounced try even though it's written in this funny way because people found it sleeky, I guess. I don't know a real good justification. It's pronounced try, but it comes from the middle of retrieval. That's so much for the name. As I said, it's a dictionary for the special case that the keys are strings. And the feature of a trie that distinguishes it from other kinds of dictionaries like binary search trees is that you traverse using parts of the key, parts of the string, instead of the whole key in one shot. Remember binary search trees, we did comparisons and walked down in the tree by comparing the entire key to some splitter keys in the search tree. Now tries do this differently. Before we talk about this assumption, let's look at the example because it's a fairly simple concept. I think you get the idea. Tries store a set of strings. Now they can also associate to each of these strings a value, but the concept remains the same. If you have a set of strings like this, you start at the root with each of these strings, and then for every character in the alphabet, there's an outgoing edge from the root. So all those edges are labeled. In our case, we only have two characters, A and B, plus this end of word marker. So from the root, there's only A and B. That's the only first character that ever occurs in those words. Right? There's only A, B, B, B. And then you recursively build the two subtrees by taking all the keys that start with an A, or all the keys that start with a B, but then you exclude this first character. You've already dealt with it. So at the end, if you do this recursively all the way down, if you only have one key left, then you put it in a leaf in this little box. And at that stage, this little box is an object in a programming language, and it could have another reference to some associated value. That's the easy part. But once you have these leaves, you can go back to the root and follow this path down. Maybe let's take an example where it's not symmetric. If you walk down to this guy, you read from the root A, B, and then the end of string marker, and that's exactly the word. A, B, end of string. All right? Is it clear what I mean by path from the root to the leaf? Or label of the path from the root to the leaf? If you're sitting at a leaf, there's a unique path from the root to this leaf. And if you read the characters that you find while you walk down this path and you put them, concatenate all those characters, you will get exactly the label that you find in the leaf. All right. So this works fine. There can be cases where you always have BB. There's never a BA or anything else after the first B. So you can have these cases where a node only has a single child. That's fine for now. There's one problem that can arise if you build these tries, and that's if one word is a prefix of another word. If you try to build the try for A, and A, it would look like this. Well, this would be a leaf already. Now I've inserted the first word, AA. Now I'd like to also represent A alone, but it would belong into this node. So I'm not sure what to do. I could allow some extra label here, or I could forbid all those cases. The easiest way to deal with this is to always force the strings to have this end of string marker. Another way to say is the set of strings is prefix free. No string is a prefix of the other. As long as we guarantee that, we will never have the situation that we'd like to store a key in an internal node. That's just to make life a little more convenient. Then we can talk about internal nodes, which don't store anything, and leaves, which always store explicitly just one key. If you're in the special case that all your strings have the same length, you also have a prefix-free set, then you might drop the end of string marker. That's sometimes convenient. I guess that's it for tries. Okay, two more remarks. We will not really talk about constructing these trees, but how you would build them manually, that's something you should know. So if I give you a set of strings like this, you should be able to produce this tree. And the way you would do it is, well, the smartest way is probably to go top down. You look at all the first characters. And then that means, there's a root with so many outgoing edges as you have characters in the first position. Then you split your set of keys into so many sets, one for each character, and delete that first character from there, and then build the subtree recursively. Shall we do a quick example, or is that clear? If no one speaks up, it's clear. A tiny example, maybe? It'll be a fairly tiny example, but maybe that's enough for now. Okay, step one is you look at the first characters. And there's only A and B. So I'll draw the root and two edges, A and B. Now, all those with an A go left. That's this, 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 and this. And well, sorry, what was that? That's the B, so this is the only thing left for the right side, so we can already put that into a leaf of its own. And for the other guys, we now look at the second character. I don't know, another color. there's A, and B. So again, we do this splitting. I'll eventually run out of colors, but so we go on recursively with those, and we have to do, you can use this. So that's the only one with a B at the second position, because it's the only one it can go into a leaf of its own. Now it remains to look at the third character in this case. And again, we have just these two options, but there's no B, so it will instead have A and $. And now every key is in its own subtree, so we can terminate the construction. So this one will go here. And a $. Goes here. Clear? All right. An interesting feature of tries is it does not matter in which order you insert the keys. What I did now was, given all the keys, build the try for this set of strings. You could also add another string one after another, so maybe we'll want to do that. We could add BBA. Now we'll obviously have to change this, so might be smart to preserve it. So what I'll do is I'll traverse along this new key in the try as long as I can go. What that means is I start at the beginning with the first character at the root, and because it's a B, I go to the B edge. And then, you know what, I'll change my mind. Let's make it a little more interesting. We go that route. We go to the left with the first character, but we can still continue on reading. So we'll just do that. The second character is a B, so I walk down this path. All right. Now at that stage, I found a leaf and I want to insert something. So this will be a new subtree here. So I'll have to replace this. And what I have to put in here is the try I would get from this key and that key. So we apply the same construction as before, but we have to take into account that the first two letters are already taken care of. So it's only the third letter that we now look at, which is A here and B here. And then again, we have two separate leaves that are left. And this one goes here. And the other one goes over here. So both is possible. You can take a set of strings and build the try for those, just top down. Or you can also add another string to a given try and add all the strings one after each other. An interesting fact about tries is that the resulting tree will not differ. It will be the same structure that you arrive at, no matter which order you use for inserting the keys. And that's vastly different from binary search trees. For sure, in the ones that I presented to you, the unbalanced ones, where, well, you might remember if you inserted things in sorted order, you get this long string that was more of a linear list than a real tree. And even if you use the balanced binary search trees that we did not discuss here, but which you might know from elsewhere, still the order of insertions has an influence, even though the height is still guaranteed to be logarithmic. But for tries, no matter what order of insertions you choose, it will always be the same tree that results from this. That's convenient. The second remark I wanted to make is, how do you query? I said tries are a dictionary data structure, so they can implement the dictionary operations that we discussed back in whatever it was, Unit 2, which in particular are get and put. I've kind of shown you how put works, because put is essentially add, unless it's already present. But I didn't really talk about how you find the key for a given, how you find the value for a given key, sorry. So how would you find the value associated with a given string in our try? You're given the string, you know it's in the try, but you want to know the value that's associated with it. Well, what you do is you follow the string left to right, following edges of the appropriate character. So you start at the root. The first character is a B, so you walk along the B edge. Maybe some color. You walk down here. The second character is a B, so you walk down the B edge. Lucky us, there was no other choice anyways. Then you follow the A edge, and then you follow the $edge. And then you arrive at the leaf that has exactly this key stored, and which also store its associated value. All right? So query or get is just traverse the try along the string you're given until you arrive at a leaf. If a traversal doesn't arrive at a leaf, that means this key is not stored. Okay, I think that's really all I want to say about tries. Let's briefly see if this is clear enough for you. It's a long question with many options, so I'll give some more time maybe. This might actually be a question where you want to discuss a little with your neighbor. That's fine, actually. It's all right. Time's almost up. Almost an even distribution, but definitely a peak for the correct answer, which is the theta of Q. Let's briefly discuss why this is the intended answer. First of all, it's important that I asked for the number of nodes and not the running time, because the running time is a little more complicated. I can come back to that. And I might have said a successful query, meaning that we actually find something there. It doesn't get stuck. So what I mean, in principle, it can happen that you start traversing at the root. Okay, from start again. Query means we walk down with our query pattern in the try, right? We've just discussed this, just to reiterate. Now, it could happen that my pattern starts with an X, and there's not even anything that starts with an X in my try. So right at the root, I know this cannot be stored in my try, and I'm done. So in a sense, what I meant was the worst case, where you have to walk down at least as much as you can with your pattern. And in that case, you walk down q steps, because we read one character each time. That was the simple intention of the question. If you think about this, it's actually interesting, because the try can be very, very big, and it can be very high. There can be very long paths in this try. But if you know that your query pattern is only 3 characters long, you will only follow 3 edges, and then you're done, depending on what the query is. Or let's suppose the query is, does any key in the try start with this prefix? Then you're definitely done. So the query time is independent of the data set size. That's actually an amazing result that none of the other data structures really achieve. Any questions about this search time? I should have added worst case, because sometimes you can stop earlier. But the important point again is you follow a path of the length of the thing you search, never more.
How can it be less than that?
The question was, how can it be less than q? It could be less than q for various sort of stupid reasons. Reason 1 could be there's no edge you can follow. Your pattern has a next character x that doesn't occur. Then there's nothing, nowhere you can go, right? The other potential reason is you end up in a leaf. Then there's nowhere you can go, but you still have learned something.
But
You have learned.
Like if it ends, we won't get the result, right?
So in both of these cases, it tells you something. If you cannot continue walking along the pattern, then there's no key in the try that has this pattern as a prefix. That's the precise statement. The second version, where you get stuck in a leaf, that means there is exactly one key in the try that has the pattern as a prefix. And both can be valuable information depending on the application. It does not necessarily mean that the search is successful in the sense that you found exactly a key that matches your pattern. But as you'll see, we don't usually need this. Okay, because it was so much fun. Here's another one for you. It's fewer answers, but it's the tougher question. Anyone still thinking about it? Shall we stop the question? Not yet? Okay, goody. Many of you got this. So maybe we don't have to discuss it in very much detail. Would one of you like to explain why that's the right answer? Oh, no, it's stuck again. So the worst case, so first of all, I'm asking again about the number of nodes. And the important part is that the number of nodes will directly translate into space usage because we have to store all those nodes in the naive way at least. And part C is the right answer because, well, there's many ways how to arrive at this. The simplest one is, suppose all your strings start with a different letter. There's a unique letter for each string at the first position. That would mean, I wish I could draw, somehow stuck. That would mean the root has n children and all of those have only one leaf, but we would continue unfolding those until we reached, oh, not the way I presented it. In that case, so forget what I said. I presented you a slightly optimized version where we don't expand the unary nodes if it's only a single node left. But suppose the first two strings have a unique character that they share, then they're all the same, but then the last character differs again. So the tree would, now it works again. You could create a tree like this, many, many copies of this. Then they share a very long part, but then they differ again at the very end, and then you have your two leaves. That's not quite as bad as having n unique branches, but you would at least have n over 2 very long branches. And if each is m characters, so that could be m minus 2 long. And we could have this situation n divided by 2 times. That's already theta of n times m. Are you wondering how the strings should look like for this? So they have notation for the strings? Not really. String 1 and string 2 are almost identical. First of all, they have some special character that only occurs at this position. And I'll use dollars because we had that for unique characters in the past. Then there's a long part that they share, and that can be very boring, could be just all A's. And then one has a B and one has an A at the end. Okay. The next two are the same, except that this first character is different. And then you copy this. So that way you can force many, many long branches. There's other ways to construct this. If you insist that this is cheating, having such a large alphabet, you can find examples without that. They're almost as bad. All right, so this is really bad because that's the total number of characters in all the strings, and that could be quite massive. So we'd like to have something smaller than that if possible. And if you think about the simple examples I've shown you, it seems they're very wasteful because there's these long paths. And that's exactly the idea behind compact tries. they're the same as the tries we discussed, except if you have a unary path, a path of nodes, a chain of nodes that have only a single child, you contract those into a single edge. So you make this a single edge here. That's as easy as it can be. As you might notice here, I used the very stupid version of a trie where you expand the unary nodes even above a leaf. In the example where we constructed them, I should change the construction. Maybe I'll do that offline. Just so that it's consistent. But what happens is all those unary paths here get contracted into a single edge. That's the only thing that happens to go to a compact trie. However, there's a small catch with doing this. As you can see on this edge, the combined label of those two edges was BB. Now in my edge here, I really only have space for a single character. Conceptually, the label of that edge should be BB. But it's inconvenient to store entire strings on each edge, so it's fine if we just put the first character here. So if you check, here's another thing that was contracted, and it got to this. We only keep the first character of this entire path label. But that creates another problem, because then we somehow forgot the second and onwards characters. So we have to be a little careful about this. The first thing that we need because of that is that internal nodes store an index. They store the how manyth character their children are. So the root stores a 0 because it talks about the 0th character in the string. Usually you just walk down 1, so after 0 comes 1, etc. But if you contracted path labels, unary paths, then you might jump. So here you would jump from 0 directly to 2. That means if you traverse in a compact trie, you have to take care of those jumps. And in particular, there's a problem all the way back. That's so much for jumping, right? I should have done this. Suppose we look for this word. This is not stored in the trie, right? There's no BAB. But if I traverse the trie, what I would do is, root says, look at the 0th character, that's a B. All right, I go there. Then I look at the second character, that's a B. Oh gosh, I found the leaf, so that's a match. But it's not, because there's a character that we didn't look at and doesn't match the character in this leaf. So what that means is, if you do the traversal in a compact trie and you reach a leaf, you still have to go through the string once again and check that all the characters really match, because you jumped over some and you have to eventually check those. Okay? So that's complication 1. You have to check another time. That's what I said with slightly trickier. But the complexity in terms of theta classes remains the same, because you still walk down one path, and what you check is not longer than the path, really. It's not 100% true. This could be very long, but we only check the length of the query pattern. Now, one remark before I'll let you go. What we buy by using this more complicated structure is that all the nodes have more than 2 children. If they hadn't, we wouldn't have kept them. They would have been part of a unary path. And that means the number of nodes is at most the number of leaves, because we always combine 2 things. So if you want to count, every node has at least 2 slots towards downwards, and it consumes one slot upwards. If you want to stick things like this together, and you want L leaves at the bottom, you cannot create arbitrarily many of these nodes, because every node adds one more of the down slots than it consumes of the up slots. So you arrive at this inequality. By forcing nodes to be non-unary, you can bound their number in terms of the leaves. All right? And that means we get linear space in the number of strings that we store, not the total length, but the number of strings. So that's theta n space, not the n times m that we had previously. Okay? That's assuming that we don't have to explicitly store the strings in the leaves, because if we do those, we're back to the same space. But next time I'll show you an application in suffix trees where we don't need that extra space. All right.